we have about 51 participants, and then and thanks to Dr. Anshu for also logging in. He is one of the speakers in the Friday session. He's from IIT. So we have about 52 participants, and then I think we can get started. Annapurna is going to.
Good afternoon, everyone. Welcome to the session on homomorphic encryption from theory to practice. Today's speaker, Dr. Ayantika Chatterjee, is an alumna of IIT Kharagpur. She obtained her PhD from IIT Kharagpur in 2016, and she completed her MS as well from the same institute, IIT Kharagpur, in 2011. After finishing her PhD, she joined Data Storage Institute of Agency of Science and Science Technology and Research, abbreviated as A-STAR, Singapore, as a scientist, and worked in the domain of encrypted database design. After that, she was a postdoctoral fellow at Indian Statistical Institute, Kolkata. Currently, she is an assistant professor at Advanced Technology Development Center, ATDC, IIT Kharagpur. Her research interests include cloud and data security, encrypted computation and analytics, hardware implementation of cryptographic algorithms. Welcome, Dr. Ayantika, for the session.
Thank you. Thank you for the introduction. Welcome to this talk. Here we will discuss about homomorphic encryption and what its journey from theory to practice. So what we expect in theory, what we claim in theory in the domain of homomorphic encryption, what we are actually getting in practice, especially when we are actually translating our real world algorithms in encrypted domain. So that will be our discussion today. So before going to the homomorphic encryption, what it is, etc., let's start with some figures. So these are some figures, some cloud data hack. That was against different IT biggies. I mean, all the names I think for all of it is known: Yahoo, eBay, Equifax, Uber, then Microsoft, Dropbox, LinkedIn, not once but twice, and even more. This list is really huge, so I couldn't incorporate them all. But if we just see the figures in the order of billions, huge amount of user accounts, passwords, personal details, credit card information, personal information, user information, all these things, these ITBKs, they have stored in the server, and it was assumed that there was at least some kind of initial level of security was promised. Still, there was data hacks, data leakages, and this is, starting from, it is basically 2013-14, the data is here, 2018, around this much of records, and many more. The number is still growing. So now we understand when we are talking about cloud and we are talking about taking the advantage of cloud, why it is important to talk about security. And the added problem with cloud is that when initially we were talking about data security, data confidentiality, the direct solution is, oh, okay, let's encrypt the data, put that in the cloud. Put for the data, the encrypted form of data from communication, etc. But for cloud computing, when we are talking about cloud computing especially, we are taking data, we are paying data to cloud services for some storage as well as for some computing purpose. So the problem with traditional encryption is that if we just encrypt the data and store them up to that much, which is fine. As I was mentioning, that when we are talking about cloud, one computing part is there. So if we go for traditional encryption scheme, the solution can be up to the storage or the transmission, where we can store the data in encrypted form, transmit the data in encrypted form. But what about this computing part? Because for computing, we have to take the data back again to the client, where we have the access to the secret key. We have to decrypt the data, and we have to do maybe for simple processing also, we have to take this much of overhead. So, and with that, the purpose of cloud computing is really getting defeated. So that is from there, the motivation comes that how we can actually compute on that encrypted form of data. And here homomorphic encryption is the solution. Okay, so we will discuss more on this homomorphic solution, fully homomorphic solution. There are different types, etc. But we will mostly concentrate on this, the final solution, the most costly solution, but most promised solution, that is a fully homomorphic encryption. But before that, we have some other low cost solution. Maybe that is, though those are better for efficiency purpose, those are better for some typical type of applications where we really mean to do it quickly. We want an efficient solution. For them, we have to compromise a bit in the encryption power. Maybe that is some sort of property preserving encryption, maybe some sort of order revealing encryption. So these limitations are there in those encryption schemes. If we are particularly focusing on typical type of operations, then it may happen we are actually supporting those applications in secure form with these type of encryption schemes. But with the optimizations, with the limitations, when we are gaining efficiency, there are some kind of drawbacks. So here we are basically considering the trade-off between the security and efficiency. So some of the schemes here, they leak some intermediate information. Some of them, they support some limited types of operations. Not all, like in case of homomorphic encryption, when we are proceeding or when we are planning, we are basically considering how we can support any kind of application in encrypted domain, any arbitrary algorithm execution in encrypted domain. So when we are actually happy with these limited terms of operations or some kind of less secure solutions, then we have some existing encryption schemes, some local solutions, or revealing property preserving. But in this talk, we are mostly focusing on the challenges of this homomorphic encryption, what we mean by fully homomorphic encryption, and when we are actually adapting this homomorphic encryption scheme for our application, algorithm translation, what are the challenges we are facing. Now, what we mean, so here the same thing as I was talking about, this is when we are talking about homomorphism, the word homomorphism, what does it actually mean? So from the left hand side diagram, maybe now it is clear what we want. So when we are talking about homomorphism, this homomorphism basically a function. Maybe we can tell a mapping between two groups. This is one, let's consider there are two groups, G and H, and we are considering elements G1 and G2 belongs to a particular group G. And we are applying some operation, some function we are performing. On this operation we are performing between the elements of this group G, like this G1 and G2. On top of that, we are performing this operation. And on top of that, we are applying this function. So by the definition of homomorphism, this is basically equivalent to applying the function first on that element. And then when we are applying this f function on both G1 and G2, and then we are operating with one equivalent operation. By equivalent, you can maybe observe these operation and these operation, they are not exactly similar. It may happen, they may be similar, they may be different, but they are equivalent operation. Now this basic definition of homomorphism, if we map to encryption cryptographic purpose, let's replace this function with some encryption function. And then this G1 and G2, some elements, some operation we are doing, we are encrypting them. This is equivalent to basically applying the encryption function on G1 and applying the encryption function on G2, and then performing some equivalent function **. So that way, basically, when we are talking about homomorphic encryption, we are expecting that these sort of elements encrypted with this homomorphic with some sort of an homomorphic encryption, and when we are performing some operation on them, it is equivalent to performing the operation on plain text data and then encrypting it. So this is the basic definition of homomorphism. And to consider our existing encryption schemes, we can see that this concept of homomorphism or homomorphic encryption is nothing new. Starting from this in 1977, when unpadded RSA was proposed, if we closely observe the ciphertext structure of RSA, this is basically one ciphertext where for a plain text x to the power e mod m, the simplest structure we are considering. So for two plain text x1 and x2, these two ciphertexts, if we are multiplicating, this is equivalent to multiplicating two plain text x1, x2, and then applying the encryption. So that way, this homomorphism was actually exhibited from it is that old. But the limitation is that here the homomorphism we are talking about is only the multiplicative homomorphism. That means we can only able to do multiplication between these two ciphertexts. We are talking here about this unpadded RSA, where we have seen that the structure of the ciphertext, like when we are talking about the ciphertext as x to the power e mod m, then this x1 e to the power e x2 e mod m, this multiplication is basically is the equivalent of saying that multiplying two plain text x1 to x2 and then mapping to this and then applying the encryption. So this is a homomorphic multiplicative encryption. Similar types of additive, multiplicative, but these are types of homomorphisms. We term it as partial homomorphic encryptions, are supported by existing encryption schemes starting from 1977 and 1982, etc. But in the 2009, people again turn looking into this homomorphic encryption, but then start thinking about this seriously about this homomorphic encryption implementation with a proposition by Craig Gentry, where he has first shown the plausible construction of one homomorphic encryption where additive and multiplicative, both homomorphic properties can be supported together. So with so from there, we started thinking on how to actually realize, how to actually translate arbitrary algorithms, because now we are not restricted with some encryption scheme that will only support with additive homomorphism or multiplicative homomorphism. Now we are actually able to support both additive nature and multiplicative nature of operations in the same homomorphic encryption. So here we have mentioned about this Gentry's proposition 2009, where a single homomorphic encryption was supported, where we are getting the flavor of both additive encryption, additive homomorphism, as well as multiplicative homomorphism. So what we mean by actually a homomorphic encryption? Okay. Let's start thinking about a simple encryption scheme, and we will see what more we need to make this scheme homomorphic in nature. These are at the left side, these are the parameters we are considering. We are considering one shared secret key, that is one odd number P. We are trying to encrypt a bit. We are actually considering here only a bit level encryption, but of course it can be extended to higher order. But M is now only a single bit, and then the ciphertext is of the form P into Q plus 2R plus M, where Q is a large number and R a very small error we are considering. Now this is the structure. If we follow the structure of the ciphertext, the structure will come later. Before that, the decryption is straightforward. We are just doing some mod P operation, then mod 2 operation, and we are getting back the plain text bit M. Now in the right hand side, we can see, now we observe closely the structure of the ciphertext. Let's consider we have taken two plain text bits, M1 and M2, and with them we are constructing two ciphertexts, C1 and C2. Of this, Q1 into P to R1 plus M1 it is the first ciphertext C1, and the second one is the Q2P plus 2R2 plus M2. Now when we are doing this two addition, C1 plus C2, this is basically, if we just simplify this terms, we are getting this Q1 plus Q2 into P plus 2 into R1 plus R2 plus M1 plus M2. Then in the next step, if we do some mod P operation, we are getting left with this M1 plus M2 plus 2 into R1 plus R2. Similarly, if we just observe down, this is what we mentioned about C1 plus C2, which is the additive, and C2 is a multiplicative operation on ciphertext domain. Here also, if we rearrange the terms and if we do some mod P operation, we are left with some error term plus M1 into M2. Here the only difference is that previously the error term was additive, and in C1 into C2 case, the error term is multiplicative. And as we it's straightforward to understand that when we are doing a multiplication, this error term will grow quickly. In compared to when we are doing one additive operation, when we are going for one multiplicative operation, of course, this error term will grow quickly. Now, if we are telling that homomorphic property of this scheme will return, or this encryption scheme will be homomorphic if this error term is always within a certain threshold. Now, what is the purpose of keeping this error term? Because if in any way after that we are doing the mod 2 operation in decryption step, but still why it is important to keep this error term within a certain threshold. To understand that, I will come back to this slide again. Can I please go to the next slide? There is one simple example, then I will come back to this slide. So we have seen that error term before getting that mod 2 operation, we are basically getting that M1 plus M2 or M1 into M2 operation. Along with that, some R1, R2 related term. We are mentioning that as error term. Now, why we want these error term to be in a particular threshold? Okay. So when we are doing in the mod P operation, if these error term related to R1, R2, if it is less than P, then it is fine. Because when we are doing this mod P operation, this 2 into R1 plus R2 or R1 into R2, whatever it may be, it will be the same. There will be no change. But what will happen if we are going for consecutive operations like C1 plus C2, C2 plus C3, C3 plus C4, C4 into C5 and so on. These consecutive operations, when we are doing, these error terms will also grow bigger and bigger. And if it happens that if this term is now greater than P, then when we are doing this mod P operation in the encryption step, the decryption step, there are two possibilities. The first possibility is that basically once we are doing the mod P operation, we are generating this R dash value. Okay, so this is basically 2R1 plus R2, or if just think in multiplicative case, it will be 2R1 into R2 minus some KP term. Now there are two possibilities. If this R dash is even, then After that, we are again doing some more 2 in the decryption step, and we will get back to M1 plus M2. So there is no problem, and this scheme will be truly homomorphic. That means homomorphic property is retaining. But what will happen? This R dash is becoming one odd value. Now this odd value means now the structure of R dash will be 2k dash plus 1. And when we are doing this mod 2 operation, basically we are getting M1 plus M2 plus some 1 is getting left. Now this addition of 1 is basically, if we think in terms of gets, like 0 plus 1, that is, when we are doing this addition or operation, we are getting 1. Or when we are adding 1 plus 1, that is basically becoming 1 0. And if we take the only 0th that bit value, basically when we are expecting our homomorphic addition result to be 1, we are getting some 0 value. Whenever we are expecting some homomorphic additive result to be 0, we are getting some 1 value. So in this way, basically, if this error is not within a certain bound, we can see that is for a bit level operation, it is basically leading to 1 bit inversion. And this bit inversion means we are getting the wrong result, and the homomorphy of the scheme is not getting retained. And this is the purpose why we are talking about. Now, can we go back to the previous slide, please? Yes. So now if we come to the right hand side, where we are just looking into this previous example, here that's why we have mentioned that homomorphy property retains till the error term is within a certain limit. And of course, when we are doing squaring or multiplicative operations, this homomorphic terms grows bigger and grows quickly, and there is a possibility it is overshooting the limit. For this reason, when we are talking about homomorphic encryption, in contrast to traditional encryptions, where we have only encryption, decryption, key generation, these functions, we have one extra function, that is basically the evaluation, where we are evaluating practical gets, and that is in turn calling some re-encryption module, or sometimes we call it for sustainability of the encryption scheme, we talk it as bootstrapping module. So this is the purpose of re-encryption or recryption module, to minimize the error level after certain operations, or to keep the error level within a certain limit. Okay. When we talk about bootstrapping, these terms we actually use interchangeably. And so for some libraries, they support bootstrapping, where what we do, we try to generate a fresh ciphertext with some reduced error level. And that is the main purpose of these. These are basically the denoising modules. The main denoising module, noise handling module of any homomorphic encryption scheme. This is the boon of any homomorphic scheme, that makes a scheme homomorphic, controlling its error, controlling its noise. And this is also, I should say, that because as we proceed with our discussion, this is also the cars of the homomorphic encryption scheme, because this makes the homomorphic encryption scheme this is the main bottleneck, performance bottleneck of any this sort of HE schemes. And second thing, this also increases the ciphertext size. In general, the whatever ciphertext size we see in our traditional encryption schemes, in comparison to that, when we move to a homomorphic domain, we see huge amount of ciphertext cycles. So that means huge memory requirement. So this bootstrapping scheme itself is a boon as a curse, which is basically contributing to make this such schemes slower, as well as it is also the reason to contribute to increase the ciphertext size in such a way that these HE schemes, they are memory hungry. So when we are actually thinking of realizing practical algorithms, realizing practical general purpose algorithms in encrypted domain, these two our main focus, that how I will reduce how I will get some acceptable performance, and how will I keep the memory requirement within a certain threshold, so it is okay to implement that algorithm within the required processor or required platform. So with this understanding, we will actually evaluate some basically two examples we will discuss in detail in this presentation. One is related to database processing, because after all, when we are whatever we are processing in cloud, there are two main types of processing. One is we are storing data, we are trying to process over that, we are getting some insight from that data. And the second one is we are applying some machine learning on that stored data. And machine learning as a service is a cloud supported service that everyone is using. So with these concept, with the context of these two examples, we will see what are the actual challenges to realize homomorphic domain applications. But before that, we need to understand that what we are getting from this basic homomorphic support, what we understand by basic homomorphic support. So homomorphic encryption related research directions are mostly twofold. The first are the most traditional research direction is to make this homomorphic encryption efficient. By making the homomorphic encryption scheme efficient, what I mean, basically researchers are targeting to improve this recryption or the bootstrapping techniques efficient, because they are trying to reduce timing requirement, making the bootstrapping or recryption algorithms efficient. They are trying to reduce the ciphertext size. So these are the basic research directions that is improving the underlying homomorphic scheme. And after that, they are basically supporting the bitwise homomorphy. I will come in detail with what I mean by bitwise homomorphy, but from the example, maybe what you have all seen, we all have seen that when we are talking, we have given the example, we have talked that this m is just 1 bit, and when we are talking about c1 plus c2 or c1 into c2, we are talking about additive or processing support, homomorphic processing support in the bit level. Okay. And the next, the other direction of research is that we will be talking about the application development and what are the challenges, in spite of the fact that AG literature is claiming that okay, you have additive homomorphism, you have the support of multiplicative homomorphism. That means if you mark them properly, you are, I mean, it is these two support is basically capable of implementing anything and everything, arbitrary operations. But as we proceed, we will see, we will basically investigate, we will basically analyze how far it is true. In spite of the fact we are having this encrypted addition and encrypted multiplication support in bit level, is it really a cakewalk to just realize one traditional algorithm or map one general purpose algorithm to its encrypted domain? So that's
Professor,
what.
sorry, there's a
Yes.
question for you in the chat window.
Yes. Yeah. Okay. Same during the
We can read
encryption.
it out.
Yes.
Yeah. Yeah.
Yes,
Should
yes.
key P be same during encryption? Yeah.
Yes. Yes, the key P is same. We are considering, because we are considering the same encryption scheme. The key is same key we are using. Okay, and with using the same key, we are generating two ciphertexts, the C1 and C2. Okay. Hello. Yeah.
Yes, ma'am.
Okay.
Please continue.
Next.
Yeah, sure. Yeah.
Yes. Okay. So can I go to the next slide, please? Yes. So to understand the challenge in the application domain, okay, I have quoted here a few lines from this book by Russell Fleming. Okay, this was the book. I mean, it was published around 2012-13 at that time, and this is a few lines written. I'm just quoting from the book. It must be emphasized that homomorphy is a theoretical achievement that merely lets us arithmetically add and multiply plain text encapsulated inside a ciphertext. In theory, this allows the execution of any algorithm, complex manipulations like text replacements or similar. But putting this to practice requires the design compilation of a specific circuit representation for the algorithm at hand. These may be a non-trivial task, and this is the motivation of our research or whatever we are discussing further. Okay, so maybe next slide. Yeah. So basically what we want to say, so this is at the bottom side, if you can see, this is the overview of the FHE tool space. So there are different, in literature nowadays, different libraries, FHE libraries. The few, then TFHE, then Kian, HELib. They are very they are very famous libraries, and we generally apply them in different application developments. But they are, in some cases, some of the libraries like HELib, SAIL, we term them, they have done some leveled homomorphic version. By leveled homomorphic, we mean up to certain level, this homomorphic, the parameters we will set in such a way that up to certain level, whatever computations, maybe addition or multiplication, whatever we are doing, the homomorphy will be retained. That means we will get the whatever result we will be getting, it will be correct in terms of homomorphic requirement. Some other libraries like few, TFHE, these libraries are another types of homomorphic schemes where they mostly support the bootstrapping, I mean, closely coupled with the get operation. Like when we are thinking about, okay, I will be doing some XOR operation, or I will be doing some basic ANDing operation. That AND operation basically comes with two inputs when I'm taking and I'm doing some TFH based AND operation. They are basically combined with the bootstrapping. Like in each and every bit level, whatever operation we are doing, we are not like other schemes, level schemes, we are not allowing, okay, up to this much of level, I know that the homomorphic nature of the scheme will sustain, will retain. After that, if I go further on processing, the ciphertext operations become noisy. That means the if after that level, after a certain level, if I again continue to process, then what will happen? The ciphertext results like C1 plus C2, if I am doing, there is no certainty that I will get exact equivalent result of encryption of M1 plus M2. That means homomorphic property will not return. In contrary to this TFHE or few type of libraries, these libraries, they support bootstrapping in each and every operation. So for this reason, whatever basic operations I'm doing, I'm sure I can go up to any level, because in each and every level, I am doing some noise handling operation. I am reducing the noise in such a way that it is, for each and every operation, the noise is within this threshold. So there is no bound to use these kind of libraries. When we are getting support of the gets of the coming from these libraries, these are bootstrap libraries, up to any level we can actually operate. But whatever library domain you can choose, types of libraries you can choose, you will see they are supporting this kind of, if we see the right hand side diagram, they are supporting some homomorphic addition blocks and supporting homomorphic multiplication blocks. In some cases, they are supporting just bitwise, like A or B bitwise. And in some cases, these A, B, the inputs, they are the packed version of some input, some or multiple bits. So whatever be the case, they are basically supporting just addition and multiplication blocks. Now, with these basic blocks, when we are translating to the next encrypted domain, maybe the next slide, please. Yes. So when we are translating to encrypted domain, what we have to check, if we just think about when we write simple C codes or any C plus coding, what we write when we have one algorithm, when we write in any C plus code, what we do basically, we do first the variable declaration, then we do some operator, we have the some supported operators coming from that language, and we use those operators and we realize our encrypted algorithmic states. And these operations, they may be separate, like single, or they may be coming inside a loop. Now when we are trying to translate algorithms to encrypted domain, we have to take care of all these operators as well as handling of loops, handling of branching statements, everything in encrypted domain. So we will see one by one that how far they are actually possible given our existing processor, underlying processor is, they are just supporting unencrypted processing because they are not ready to handle this encrypted processing. So maybe we will take one by one some few examples. Maybe next slide we can go there, we will discuss more on this arithmetic operators. Here I have mentioned that what types of operators we have to take care of. So maybe one or two, every operator design I cannot discuss here because we have limited time. So one or two examples I will give that will to make it clear that why this is not so straightforward. Let's start with a simple loop handling. When we are thinking of loop handling, what we do basically, just simple for loop, while loop. When we write, what we do some condition checking. We have some loop index, we have some loop counters, and we have some loop termination conditions, right? So what in each step we compare with these counters and this loop termination statements, and we check that if the counter is lesser than the loop termination condition, we actually execute the loop, otherwise we come out of the loop. This is the general structure. Whatever language we use, this is the basic concept. Now what will happen if this loop counter is the output of some encrypted previous processing output? Let's say you have done some encrypted addition C plus D and E is your output, and then based on if you are checking, you are trying to execute a loop, if E less than some F, and this E and F both are encrypted. If this is the case, now your loop counter and loop termination condition, they are basically getting compared with some encrypted module, and they are generating some encrypted output. Now this encrypted output is basically your final loop termination condition. Basically, if in general case, your traditional processor, they check this termination condition, this comparison output, and based on that, they take the decision that whether to stop or execute the loop. Now here in case of encrypted domain scenario, this comparison is basically giving you some encrypted output, some random number, and your unencrypted underlying processor doesn't know. It will always feed that some non-zero value, and it will go, if we just blindly compute the loop, try to execute the loop with this encrypted values, it will basically generate, it will go into some infinite loop. So traditional or direct straightforward loop handling will not work in this domain. Next comes a few simple operators. Just two operator examples I have taken here. One is the shift and add algorithm that we generally use for our multiplication realization. What happens in these cases, this shifting or addition, this is bit dependent. Like if you have 0 bit, you maybe do only some shifting. If it is 1 or 0 both, you do shifting and addition. Now when you are talking about this encrypted domain, all this encrypted 0, encrypted 1, they are basically generating some random number. So in both the cases, you cannot take this advantage that okay, for this is my 0, So I will skip the operation, or this is my one. I will do the both shift. I will be doing both shifting and addition. Here the overhead is that if you go directly, if you choose to go for this kind of shift and add algorithm, you are not getting any advantage that you were expecting in unencrypted domain, where you are skipping some operations based on the bead values. The third example in the left side is basically for simple division implementation. Just two examples I've taken here, shifting and the multiplication and division. So when in case of division, the problem is if your numerator and denominator, what we do in division, if we just think the division is our repeated subtraction, we know that the subtraction will stop when this comparison result will give you some definite output. In the left side, if you see that this loop while n greater than d, so d greater than equal to d, so numerator denominator of our division. So this comparison, again, when you are doing one encrypted division, your numerator denominator both are encrypted and they are generating again some encrypted output for after this comparison. So in that case, this while loop, your underlying processor will never know when to stop this while loop, and it will again go to some infinite loop. So again, what I mean to say, the traditional way of division realization also will not work in this case. I've just taken here one or two examples because maybe in this paper, if anyone is interested, you can go through that. So all the operators this way, we have to take a closer look. Otherwise, the traditional, in spite of the fact that we are claiming that whatever we have with the support of bitwise homomorphy, we can do everything. But the traditional implementation, direct mapping of them will not work in this case. Okay, so we will take some more examples now, application specific, in case of SQL processing and in case of um, machine learning, because these are the, as I mentioned already, these are the two main applications that we expect from cloud. These are the two main processing requirements that we expect from cloud. So when we are storing we are having a database in cloud, we are storing the database, the values in the cloud, in that database in encrypted form. What we will expect, we will expect the general kind of SQL processing, what we do in our normal database. We want to also do the same thing on that database. Now, where's the challenge for that? The first challenge, basically, I am trying to show one, maybe I will, if time permits, I will, at the end, I will show one demo on this. But first, I want to tell the what is the problem. Like when we are doing this SQL processing, let's say simple queries execution, what we are doing, we are checking a particular condition. Maybe just hello Annapurna, I want to share a screen a bit. Okay, I want to try if it is possible, then I can show the demo so everyone will understand clearly. So what we are doing here, we are just taking this but encrypted SQL query. Okay, so we are doing this encrypted query execution where we have, these are the typical types of query, just very simple queries we have taken here. So we have a one encrypted database ETB where we have some columns, and one of them is the age column. Here, if we give this some value, let's say 30, we will execute, and you can see here it is actually executing in the encrypted domain. Just wait a bit, it will take some time to complete. We have just restricted to few rows for the demo purpose. It will not take much time. So what we will see basically, when we'll see the result, we will see that the encrypted database we have uploaded that in the cloud, and this sort of encrypted processing we are doing. Yeah, it is there. No, still not there. It's executing. We will see, we will get back here. It is done. So this is on a standard data set. These are the columns we had. Okay. We have given the condition on this column age, and this is the age column. And then on top of based on that, these are the results we have got. And if you see the results, only one valid row we have received. Valid row means where we are getting some values, that is according to other columns, and all other values are all zero values. I will highlight this point, and I will explain that why it is the requirement of to get this kind of values, or why we are getting some invalid values along with the valid value. Now, when we upload the data set, here just for this demo purpose, we have taken this few rows. We are encrypting them and uploading them. And then in the cloud side, we are comparing them with the edge. That is the column we have selected. And we are taking back the rows which are basically satisfying the condition. But if it happens that any adversary is doing the same computation in cloud.
Professor, in the meanwhile, there's a question by Siddharth Alal. He asked why
Yes.
we are zero rows.
Yes, that's exactly that point I will highlight and I will explain. Okay. Exactly, that is a main challenge here, and that is the main problem we are focusing here. First of all, I will go to that diagram, and I think it will be easier to understand. Okay, just give me a minute. The reason is that when we are doing the encrypted comparison, we are setting the values in this way that if this condition, like for some column, the age is really less than 30. If that is the case, the row will return the valid values. Otherwise, the row will actually return the zero rows, because this, okay, I will go with that maybe, hello. Now you observe, this is the left hand side, the topmost is our original database. Okay. We are having different rows and columns, etc. And how we are selecting a particular value? We are selecting based on some encrypted multiplexing. Okay. What we mean by that? We are basically, this is the age column from each row we are choosing, and another input to this condition checking module is our whatever input we are giving. Like here, some age value 30 I have given, and encrypted value of the 30 is going. And here one encrypted condition checking, that means this greater than, lesser than, whatever we are planning to check according to our select query condition, that condition is getting checked. And this block will output this E out. I hope you can see. This is either 1 or 0. Encrypted 1 or encrypted 0 to be specific. Now this encrypted 1 or encrypted 0 will act as the selection line, where one input is all encrypted 0 and the other input is the row value. Now, if this condition is getting selected, if this condition checking is successful, that means your age is really less than 30 or whatever condition you have given, then the selection of this mask is 1 and it will select this row value. Otherwise, the value is 0 and it will select this encrypted 0. This is a simple multiplexing concept what we use. It will use that and it will store that to resultant data sets. Now you can tell or ask in this way that whether it is an implementation limitation or can we do in some other way so that we can only get the selected rows or we can only get the valid rows. The answer is no. The reason is, you just think in other way. Maybe in the one of our paper there is a formal proof in the book also. If you can read, if you think that you can actually, one adversary is giving this condition and he is actually getting a result where if the condition is getting satisfied, and if he is not the condition is not getting satisfied, he's not getting any row back. From there, the adversary will get the idea, okay, whatever 30 value here he or she may have given, the age value is actually less than or greater than from the given condition. And that will, there is a formal proof you can check later on. It will lead to some chosen plaintext attack. Okay. From there, adversary with a probability 1 can tell that the condition, this E out, this condition checking result, this is an encrypted. So this is one encrypted value E out, but the adversary, when he has chosen some, some threshold, let's say 30 is given by the adversary, and now he's just working on a single row. The row age value is encrypted. Still, from this comparison result, this E out, if anything is not getting returned, then adversary will be sure that, okay, this E out value is the either the encryption 1, if he's not getting some value, that is the condition is getting satisfied or not satisfied. Based on that, adversary will get the idea this E out will be encryption on 1 or encryption of 0. And in that case, this is basically leading to some chosen plaintext attack. So the main thing is that the idea is that anyway you do this implementation, the final row size, whatever the resultant row size you are getting after each and every selection query, that will be exactly same with the original resultant dataset. I hope this was the question, right? So that's why this, otherwise there will be no guarantee of the CPF security. And this all the FHA schemes we are using, this is basically this CPA attack secure. And based on that assumption, we can conclude that this is not any implementation flaw. We have just implemented in this way, and we have implemented this encrypted 0 in that part. But whatever way you store, you cannot reduce the number of rows. And this is the main bottleneck of, straightforward implementation of this select query. Yes, there's another question. Just a second. Yes. Will we receive all rows for each query that is executed? We will receive all, let's say, take it in the simpler way. If your initial dataset is, database is having n rows, in the resultant query, you will, query result, you will receive n rows. But if among them, let's say, 5 rows are actually satisfying the condition. If for 5 rows you are having, for our case in the demo, maybe you have seen only 1 row is satisfying the age less than 30 condition. That will return the valid data, like non-zero data. Otherwise, all the other rows, whoever not satisfying the condition, will return the encryption of 0. Yes, here all invalid data is represented by 0 rows. Okay. Okay. So this is the main, and this is a one important point we want to focus. Otherwise, that's why this implementation is free from volume attack. But what is the main disadvantage? It requires huge data transfer overhead from cloud to client side. That means when you are actually doing your query and you are the client is getting back the whole data set, the size and the whole data rows, the client should decrypt, then it will remove the all 0 rows, then they will get back the original result that is required. So of course this is not as per, right? For all the practical huge databases, the number of rows may be huge, so that will incur huge transfer overhead, also the huge processing overhead in the client side. So for that, we have proposed one solution. Maybe we can go to the next slide, please. So this is the modified representation, we have proposed, where see, we cannot, in the client side, of course, the resultant data set will consider, we should have all the rows. We cannot reduce that. But what we can reduce, the transfer amount and the processing amount in the client side. And we have tried that. So for that, what we have to do, if the rows are arranged in this way, that all the valid and all the invalid rows are together, like they are not separated, then whenever we are transferring any chunk from cloud side to client side, there may have some invalid rows and some valid rows. And after the whole transfer, the client will never be sure, and the total decryption, client will never be sure that, okay, now we have gone exact number of valid rows. I hope so far you understand that by valid rows, I mean the non-zero rows. So for this reason, what we have done here, we have basically considered taken one stack-like approach. Okay. So whenever we are processing, see, maybe in this direction, the upper part is doing the same thing that I have explained in the previous slide. Basically, the RDP data we are choosing, no matter, it may be or zero, it may be non-zero. But the bottom level, we are maintaining one stack, and this top is the stacked top variable. You can think it as a form of stacked top variable. So what we are checking, in an encrypted way, we are checking the stack top is actually going up if the previous value, that means this E out, is a valid condition. That means if there is a valid condition selection, that means one valid row is coming and sitting in the stack. And then only we are increasing the stack to next top plus one value. If not, the top value will hold the previous location. In this way, what will happen? Now, after the whole processing of all the rows, still the initial stack size what we have, that is the sum part will already be filled with 0. And the rest of the part will get updated with valid rows. So what is the advantage now? Now my valid and invalid rows, they are arranged separately. But in cloud side, if some adversary is observing this processing or that stack, still all the non-zero or valid or invalid rows, both are filled with some encrypted zero values or some encrypted non-zero values. So for adversary, it is the same. Its adversary is looking that as a stack of random numbers. But when the transfer is taking place from cloud to client side, maybe we can now allow some small chunks, some chunks with few rows. Okay, let's say we have n rows together, total as a whole. Now we are just taking a chunk of m rows. So what will happen? Maybe first few chunks of m rows, when the client is decrypting, if client is getting non-zero values or all non-zero rows, then it will understand that it may happen for next chunks they are having some non-zero or zero values. But if the client is receiving one chunk where it is having some non-zero values and the top is filled with one or more zero value rows, that point of time client will understand there is no purpose receiving any more chunk from the client. So the communication will stop there. So that way, if we can, let's say we are basically translating, let's say 2 or 3 chunks of em rows, and after that communication, client is, after decryption, client is getting at least one invalid row, client will understand that all the rest of the rows are filled with zero values. So there is no. So in that case, the communication will stop. So basically what we are doing here, for this client compatible data transfer and for reducing the communication overhead. Yes. And again some question, one second. By grouping valid and invalid data together, no further information revealed to the adversary about the data. No, why not? The adversary, you may ask that adversary is also watching the communication. Correct. Maybe adversary is sure that all the considering the among n rows, few rows, the all n rows are not satisfying the condition. It may happen this much of information is reducing. That is okay. I'm coming to that next question. Let me first complete this one. So, but the thing is that when, let's say, first chunk of m rows are coming, thus that is filled with total invalid rows, filled with valid rows. Second chunk also filled with valid rows. The third chunk is filled with 2 or 3 valid rows, and then rest all are 0 rows. Now adversary will not have the idea that for the last chunk how many rows are valid and how many rows are invalid. For that, that definite information will not be present with the with the adversary. So exact volume attacks are not possible. But of course, the some amount of decrease, some amount of information will be there. But with this optimization, we are basically allowing the we are reducing the communication overhead, also the data structure and processing requirement. Okay, FHE should be similar architecture. Like, will it be possible to use symmetric key? Yes, there are also different versions of symmetric key FHE. In fact, and similar those symmetric key FHEs can be also extended to that public key version. So both are possible, and in both the cases, it will be. Yes, sir. So essentially, grouping is more for optimizing data transfer from the server to the client. Yes, correct. Grouping is for optimizing data transfer as well as reducing the processing requirement in the client side. Okay, maybe that's all. Okay, maybe the next slide, please. Okay, so similar SQL query processing, like this is one example of how we are doing the like. Then we have join, etc. All these queries. I'm not going into the detail because of shortage of time. But we will see this is the join operation where we have seen that if we just directly go for detailed joining, right, column by column matching with an element per element matching for each column, then it will be huge performance over it. So in this case, the hashing based technique, like for few columns when we are preferring join operation, so there it will be better for to store some extra information like some hash values. Otherwise, the communication overhead is too much, and that makes this join operators impractical in FHE domain. Okay, maybe next slide. Okay, this is another example. This is for the power computation. Okay, like in SQL query processing, in some case we compute the power. In general, power computation also, it is not only specific to SQL query. So in case of power, what we want to do, we want for, let's say, a to the power b, a simple we want to compute. So if a and b, among them b is unencrypted, so that is a very straightforward. We can consider a loop, and there we can do encrypted multiplication a few times, and we can compute this a to the power b. But the problem comes when my a and b are both encrypted, and there we have to take one extra step, extra care to check where this computation will stop. Otherwise, it will again lead to some infinite loop. So for that reason, this is one proposition. What we have proposed, that we will take one range. Let's say we will decide one range of the power. Let's say b is 8. So when we are computing a to the power b, let's say b is 8. Okay, but we will be fixing a range maybe of 15. Like whatever may be the b value, we know the maximum possible. This will be application specific operator designs. Otherwise, this type of implementations are not feasible in homomorphic domain. So what we can do, we can take a range, let's say 15. We know that maximum value of the power will be 15. And but in actual case, we want to compute maybe b is equal to 8. So that means after the actual power has been reached, actual exponent value has been reached, there should not be any update on the final output. So to take care of that part in encrypted domain. Basically, if you see this upper part of the circuit, every time we are computing we are basically checking whether my exponent value is lesser than the range value. And that check is also being done in homomorphically. If the range exponent is lesser than the range, then only the final power value is getting updated. But if that condition is getting false, then the previous value is getting retained. That means if you have computed up to a to the power 8, after that, your execution is taking place, homomorphic execution is taking place, you are computing a to the power 9, 10, etc. But your final power, final result is only holding the a to the power 8 value. So that way we are not allowing any erroneous computation. But here it is possibility of computational wastage, because after that a to the power 9 to 15 computation, it is basically a huge wastage of computation. But at least to make the implementation feasible, this is the workaround we are performing. Otherwise, the implementation of the direct a to the power b computation, where your base and exponent both are encrypted, that is basically infeasible in encrypted domain. So there are many such operators. Maybe in the paper we have detailed with respect to the SQL processing. Now I'm skipping that discussion. Yeah, there are absolute computation. Maybe we can go a bit. This is the update query processing, where we have, there is the requirement, like if any adversary is can do this update query processing, then they may have some malicious effect on the database. It can just, with some garbage value, it can update the database. So there should be some access control. But the problem of incorporating this access control in encrypted domain is that your overhead should be very low. Like whatever encrypted processing you are doing, along with that, the access control related operational overhead should be very minimal. So we have actually proposed one protocol here where we just have some bitwise operation we are adding as an overhead, and that is giving the effect of this access control. So that when there is an update request, at least there is a first check whether that the requester is having the proper access or not to perform these kind of sensitive queries. Okay. So these are few examples, few operators we have discussed, and I think this is what I want to highlight, that for each and every operator, the demands are different. And maybe we can see the similar thing to the, maybe we can go to the next slide, please. One example I will take from the machine learning also, because so this is whatever example so far we have discussed. This is from the SQL query processing. Now this one single example I will take from machine learning as a service, because that is another very prominent application we get from cloud. So here a very simple machine learning model, that is a KNN model, k-nearest neighbor. So I'm not going to the details of the machine learning algorithm and what are the implications. I'm just focusing on the operational requirement, because mostly that operational steps we have to map to the encrypted domain. So in that KNN requirement, two important operations are, one is we can see sorting of the distance, and the second, first one will be we have to compute some distance between the training data and the test data. And the second one is the sorting of the distance of import. Basically here, like in previous SQL order by operators, we need the concept of sorting to be realized in encrypted domain. So the straightforward implementation, if we go for the swap operation, because sorting is after all swapping. You have some lower value and you have some upper value. And these, if the upper value is greater than a lower value, we do not have to do anything. But if the lower value is greater than upper value, there should be a swap. Basically, that is the very basic idea of when once we go for the swapping based sorting techniques. So that also we have realized with this encrypted sorting, where we are basically doing taking the difference between two distances with the subtraction operation, and then again we are applying one marks, and based on the subtraction result MSB, because MSB in 2's complement representation will be 0 or 1. Based on that we can understand whether this one distance is greater than the, like, upper value is greater than lower value, or or the opposite one. So in that way the marks is acting as a selection, and it is putting these distance in the proper position, where if the distance either this first input is greater than the second input, then this subtraction result MSB will carry the 0 value, and it will select the first input, and it will place that first input to the upper position. This way the encrypted swapping will take place, but the important thing is that the whether the swapping is actually taking place or not, that will never get revealed. So in that way, the flow of the swapping, the flow of the sorting, to be specific, will always remain hidden, will always remain encrypted. But the actual whenever, another question you may ask, that whenever there is already the position has in a particular position in upper value, some value has been placed after this swapping operation, and before there was some value present in that particular location. So adversary may do a bitwise check, and they can get some idea that whether a swapping has been taken place or not. That is some kind of also leakage. But here the one important observation is that all these upper values and lower values, when it is getting before and after the swapping operation, they are bitwise different. That means, let's say C1 and C2. These two ciphertexts, they are basically the encryption of same plain text. Yes, they are basically the encryption of same plain text, but they are bitwise different because they have gone through this intermediate homomorphic processing. And for this reason, this is the way, in spite of the fact that adversary is probing a particular location, it will not be clear to understand that whether there's the actual swapping has been taken place or not. And that way the CPS security, so that's the security or the flow of the sorting technique is also getting preserved. Okay. So similar observation, we can go to the next slide. Okay. So the next important concept is that in general, when we go for sorting, we do not prefer like these type of sorting techniques like bubble sort. We prefer the partition sort. Now here to observe this partitioning, can we actually do in encrypted domain, and if we can do, whether it is leaking in information or not. So if we consider we assume that, okay, if we really can do partition based sorting in encrypted domain, so what will happen? The adversary will have some access to some partition oracle, and this partition oracle will be giving the idea that one particular value in that array, maybe where the sorting is taking place, is either greater or lesser than the pivot element. So adversary will not have, because pivot is also encrypted, adversary will not have the pivot information. But at least this information will be clear, this pivot is greater or lesser than this particular element. And that is also one sort of leakage. And in this paper, there's a detailed proof that these can also lead to some chosen plaintext attack. And since FHE, the underlying schemes we are considering, these are ECPS secured, these kind of partitioning is not possible. So the important takeaway is that the partition-based sorting techniques, though from our traditional knowledge, sorting knowledge, plain text knowledge, we know that this is, we can, those are better in comparison to sorting techniques like bubble sort, where we need to have the order of n square complexity. But these partition-based techniques, partition-based sortings, are not possible when we are working with encrypted domain. So there are many such discussions, and for that we gradually take one by one machine learning models. Also, this is one discussion on KNN, when we have chosen the distance. When we are talking about distance computation, there are many available distance computation algorithms. But for the sake of the simplicity and the sake of the performance, because the more we will try to operate, the more we have to handle FHE gets, and the more we will be calling the bootstrapping. So this is not very much desirable. Desirable in terms, by that means desirable in terms of performance, because more bootstrapping will incur more performance overhead. So that way, when we are actually translating these algorithms, the main challenges we are facing, the first thing is that feasibility. Though there is a theoretical claim we can do everything and anything, considering our underlying processor, there are few limitations. The second limitation is coming from the algorithm we are choosing, that is how we are make it performance worthy. Like maybe we can go to the SVM example, maybe the next example. Here, the SVM prediction, maybe the previous slide, the SVM implementation, the prediction step demands this type of, when we are talking about weight and the text input, both are encrypted, this type of huge amount of multiplications. Now, homomorphic multiplications, as we understand, it is already costly. So how to reduce that performance cost? For that, we have exploited the fault tolerant nature of the machine learning techniques. So we have basically replaced this addition and the multiplication blocks with some approximate computing blocks. There, what we are basically doing, we are reducing the full adder to some compressor, encrypted compressor, where we are removing some low probability term. That means this P0 into P1 into P2, if we are reducing this, we are just ignoring that term. We are basically incorporating some error in the overall computation. But what is the advantage? For that, we have checked that the overall prediction accuracy is maybe reducing 3 or 4%, but that is tolerable. So the overall accuracy is reducing, but the overall performance gain is comparatively huge, where we can do now the SVM predictions within some 5 or 6 minutes. So that is, whereas with that accurate multiplier, that is more than around 25 minutes for a single prediction when we are talking about FHS. So these are the few techniques we have discussed. Maybe in the slide we had more, maybe one next slide we can go for linear reduction. We have seen that, maybe next to next slide together we can cover, we have a shortage of time. So there we have seen that, maybe the previous one, yes. In the linear regression, we have observed the one division that we cannot avoid. But encrypted division, as I already mentioned, that is infeasible. So we have chosen one non-restoring version of the division, where we are basically uploading on extra information to the cloud. That is the bit size of the quotient. Now this is, since not a very significant information, or that we assume that will not leak much information, but with the upload, we just allowing that much of information in the cloud, actually we can implement, we can make the encrypted division feasible. Similarly, maybe next few slides. So maybe we have explored in DNN computation, where the requirement DNN, there are so many layers, and also the different types of activation functions. We have to take care of them separately, and some of them are still infeasible. But with some architectural tricks, like arranging some data and packing them, and making some bootstrapping, like we have packed in such a way where with the packing technique, we are reducing the number of bootstrapping. And for the whole packing, we are allowing just one bootstrapping. And in that way, just I want to see these results. We do not have much time to discuss the whole technique. If in the right hand side, if you observe the timing requirement, you can see from 80 hours for the same NUFHE library. This is a GPU supported library of TFHE. I mean, GPU version of TFHE library without bootstrapping, the requirement of 80 hours, where it has been reduced to 2 or around 3 hours. So basically, if we can control the bootstrapping part, this is the main bottleneck. As in the starting I was telling, that is the advantage of homomorphic, and that is the curse of homomorphic encryption. So maybe there are different strategies people are taking nowadays. The bootstrapping part people are separating, and some 1 or 2 recent works are there where people are taking the bootstrapping part in the hardware. Maybe we can go to the next slide, and that is my that is the detail. That is my last slide actually. So there, bootstrapping, if we take only that part to the hardware with some FPGA support, and if we think about some software hardware co-design, then the gain may be expected more. And this and with this we can understand that FEG, this mammoth task, basically not a single this is not a problem of only the mathematical problem. This is not only an architectural problem. That is not a software problem or only a hardware problem, because underlying mathematics we have to optimize it, make it I mean more optimized, so that we can improve the bootstrapping time. We can reduce the performance requirement from that part. And on top of that, we have to, the software implementation is important with the supported FEG gates, where we can actually check how different types of basic algorithms we can actually translate to encrypted. And also in doing so, we are having some limitations from our coming from our underlying softwares. So in spite of the fact, whatever backing techniques, whatever parallelization we try to support, inherent this processing, software processing, they are having their own limitations. So in that case, if we can take this bootstrapping part to the hardware, maybe that the software hardware co-design together can improve the overall performance first. So that's all with this note. I stop here.
Thank you from our end for interesting and an important talk. This topic is very important, right? And you covered, you introduced and also covered the implementation aspect, important applications. Thank you very much, Professor Ayantika Chatterjee.